Everybody, hello, my name is Nick Larson. Today is October 18th, 2019. Happy Friday, everybody. We're going to have a little Friday fun day today because it's Friday, and from now on Fridays, I just want to have fun. So that's what we're going to do. The way this is going to work is I'm going to choose a project that I think is fun, and then we're going to do it. I would like to start off today by giving a shout out to a bunch of people. First off, C Sharp Fritz, thank you so much for the raid yesterday. 82 people, unbelievable. I mean, absolutely incredible. I'd like to thank Vishir HD for the follow, Killer Coder PT for the follow, Lucky Number 11 for the follow, Desert Desert Griffin for the follow. Electric Demon for the follow, Furris for the follow, Callow Creation for the follow. Oh, damn, you gotta edit this. I always do this. I'll get back to that in a second. Friday, fun day. And we're gonna do, Monte Carlo tic-tac-toe game. Coding, it starts now. Alright, there we go. Alright, see how I did that? Alright, great. Okay, let's refresh that one more time. Great. Okay. Give me just a moment. I lost track. All right, Furris, Callow Creation, Tenno Diablo, thank you so much for the follow. M Holloway 24, thank you for the 50 bits. I really appreciate that. C Payette, thank you so much for the 200 bits. That is amazing. I'm out of my mind. Thank you. Zav, thank you for the follow. Two Wolf Design, thank you for the follow. Wanadazecha. Yep, thank you for the follow. Return to Dust, thank you for the follow. Dr. Argus, thank you for the follow. Data SKS, thank you for the follow and for hanging out in chat right up until the very end there so we could work through some of the problems we were dealing with. And then Rexo Gamers Switch, thank you so much for the follow. I really appreciate all of that. Let's go ahead and get started. I want to let everybody know that I have never in my life implemented Monte Carlo tree search before. And we're just going to roll with Wikipedia on this one. So conceptually, I understand Monte Carlo tree search. The idea is that you know nothing about a game, and so you basically have a tree of states where you're in a state, and then you have a bunch of different actions you can take. And each of those actions leads you to a new state. And when you're in that state, you want to decide which action you should do. And the way that you decide which action you should do is by basically simulating games and then going down the path that leads to the best outcome on average. And that's the plan. That's the idea behind it. And then if we get into the actual steps, let's go ahead and take a look. Principle of operation. The focus of Monte Carlo tree search is on the analysis of the most promising moves, expanding the search tree based on random sampling of the search space. The application of Monte Carlo tree search in games is based on many playouts, also called rollouts. That's you basically just play a bunch of random games, and then when you're done playing a bunch of random games, you just choose the best outcome for the next move. In each playout, the game is played out to the very end by selecting moves at random. The final game result of each playout is then used to weight the nodes in the game tree so that better nodes are more likely to be chosen in future playouts. The final game result of each playout is then used to weight the nodes in the game tree so that better nodes are more likely to be chosen in future playouts. And I think that's the key point here. Is like each time we play a random game, it becomes a little bit less random. We start going down the path of that leads to wins most time to explore that path more fully. All right, the most basic way to use these playouts is to apply the same number of playouts after each legal move of the current player. Then choose the move which led to the most victories. All right, so I'm in state, I'm in this state, and I can make these 3 actions. So this is saying for each of these 3 actions, play the same number of games, random games, and then choose whichever one of those ended up having the best chance of winning. Yeah. The efficiency of this method, called pure Monte Carlo game search, often increases with time as more playouts are assigned to the moves that have frequently resulted in the current player's victory according to previous playouts. Sure, that makes sense. Each round of Monte Carlo tree search consists of 4 steps. First is selection. Start from the root R and select successive child nodes until leaf node L is reached. Okay? Okay? Until leaf node L is reached. The root is the current game state, and a leaf... the root is the current game state, and a leaf is any node from which... The hell's a freaking spider in here? The root is the current game state, and a leaf is any node from which no simulation or playout has yet been initiated. The section below says more about a way of biasing choice nodes, biasing choice of child nodes that lets the game tree expand towards the most promising moves, which is the essence of Monte Carlo tree search. Expansion. So selection is sort of weird. That doesn't make sense to me. It says the root, and then you just continuously take nodes until you get to L? I would have thought you just started... Well, I guess if you have information about them, sure, okay. Expansion. Unless L ends the game decisively... Oh, this makes sense. So we've looked at all of the child nodes, and we have determined... Alright, yeah, we have looked at all of the child nodes, and we have determined that, we're right here, and we're looking right here, and right here, and we see that you have a 7/10 chance of winning, a 3/8 chance of winning, which is what, 675, so it's a little bit less than 7/10, or a 0% chance of winning. So you take the one that has the best chance of winning. This is your opponent's move, and they're going to take their best chance of winning. They have a 50% chance to win here, they have a 5-6% chance to win here, because this is my chance to win, so my opponent's chance to win is 1 minus this. So we choose the one that has the highest, then I choose the one where I always win. Wait, that doesn't even make sense. Hold on. Why would my opponent not choose the 2-4? Okay, we're going to take a look at that. I don't actually know the answer. This isn't making 100% sense here. Maybe it'll explain it in more detail. Alright, expansion. Unless L ends the game decisively, for example, a win, loss, draw for either player, Create one or more child nodes and choose node C from one of them. Child nodes are any valid moves from the game position defined by L. That's right. So you just say, get me all the next possible positions we could be in, and then randomly choose one. Okay. Child nodes are any valid moves from the game position defined by L. Simulation. Complete one random playout from node C. This step is sometimes also called playout or rollout. A playout may be as simple as choosing uniform random moves until the game is decided. For example, in chess, the game is won, lost, or drawn. Sure, that makes sense also. Backpropagation. Use the result of the playout to update the information in the nodes on the path from C to R. So this means, like, if you won, then you mark it down. Oh, wait. No, this really doesn't make sense to me. Okay, this graph shows the steps involved in one decision, with each node showing the ratio of wins to total playouts from that point in the game tree for the player that the node represents. In the selection diagram, black is about to move. In the selection diagram, black is about to move. The root node shows there are 11 out of 21 playouts for white from this position so far. It complements the total of 10 of 21 black wins shown along the three Okay, this is starting to make a little more sense. The root node shows there are 11 wins out of 21 playouts for white from the position so far. It complements the total if white loses the simulation, all nodes along the selection incremented their simulation count, the denominator, but among them, only the black nodes were credited with wins, the numerator. If instead white wins, all nodes along the selection would still increment their simulation count, but among them, only the white nodes would be credited with wins. In games where draws are possible, a draw causes the numerator for both black and white to be incremented by 0.5 and the denominator by 1. This ensures that during selection, each player's choices expand towards the most promising moves for that player, which mirrors the goal of each player to maximize the value of their move. This basic procedure can be applied to any game whose positions necessarily have finite number of moves and finite length. For each position, all feasible moves are determined. K random games are played out to the very end, and the scores are recorded. The move leading to the best score is chosen. Ties are broken by fair coin flips. Pure Monte Carlo game search results in strong play in several games. It converges to optimal play as K tends to infinity in board filling games with random turn order. For instance, in Hex with random turn order. DeepMind's Alpha Zero replaces the simulation step with an evaluation based on a neural network. Okay, let's do this. So previously, let's close this. I had actually started a Monte Carlo tree search game. Repo, whatever you want to call it. And I already have a few things implemented. Let's take a look. All right. I already have, you start with the program. You go to the left so you can actually see what's going on. And in the program it says, do the test to make sure that, you know, all of my game state is set up correctly. And then play a game. And let's just make sure that that actually works. Because there's no guarantees. Not what I wanted to do. Terminal, new terminal. I don't actually want a new terminal. I want the first terminal. Okay. .NET build ls cd space src ls cd space mt mc ts ls .NET build .NET run. Unable to run your project. .NET version. Ooh. Ensure you have a runnable project type and ensure .NET Run supports this project. A runnable project should target a runnable TFM, for instance, Net Core App 2.0, and have an output type exe. The current output type is library. Really? Interesting. Is that new? .NET. Okay, .NET Core 3. What am I looking for here? Output type? Console app. How do we go? Console app CS proj. Oh, weird. Output type exe. I guess so. Maybe that. I mean, whatever. Ah. Let's try that again. Okay, well, I didn't see any errors or anything. Is it supposed to have printed out errors? If there's a failure, then throw an exception. If there's a failure, then throw an exception. Okay, so yeah, I think we're fine here. So terminal tests seem to be fine, and then if we play the game, I believe you're going to see it down here at the bottom. It's asking me which move. This is the current state. Which move would you like to play? Please select the successor. 0, 1, 2, 3, 4, 5. So we're going to go with 4. Okay. This is the current state. Now please choose a successor. All right, and this is the idea. You go back and forth. So this is just two humans playing at this point, I believe. Yeah, console player, console player. So that's sort of the issue at the moment. And now what we want to do is we want to figure out how to make one of these a Monte Carlo tree search player, which you can see I did a great job of actually implementing, because I didn't actually implement it. All right, where is console player? Okay, console player. So I think conceptually, I want a Monte Carlo tree search player, And then I basically want to have them have an instance of Monte Carlo tree search for this game, I think. We've got player, console player, most of which is actually printing out the board. Probably don't want to do a string result. It's not really that important. Okay. So player takes an I player, which takes an I game, and the successors. Okay, let's just do that. Let's make a Monte Carlo tree search player. Let's go new file. Monte Carlo tree search player. Namespace MCTS. Public class Monte Carlo tree search player. I player. Let's have it implement this. Implement this interface. Name. How do I do the name on console player? Just get set. Sure. Let's just do that. Okay. That's done. Okay. Now we have this. And I think what we can do is just have like private Monte Carlo tree search MCTS equals new. Maybe we'll go something like public Monte Carlo tree search player MCTS equals new Monte Carlo tree search. And then effectively what we want to do is have something like Monte Carlo tree search dot let's see. Okay. And let's have I think we can do this entirely generic. I think we can do this entirely generic. Like we don't need to know the actual game information at all. So we just have something like public iGame or maybe even iGame. Select next action. iGame current. Maybe? And then this would be throw new not implemented exception. System. Okay. iGame, no, current state dot expand successors is terminal. Sure. Let's go return mcts dot select next action of current state. Or okay, var selection equals this, and then we just say if successors, really I just want to check if it's in the successors, but I'm not even going to worry about that for now. To do, check that it chooses a valid move, and then just return selection. Okay. And then the entire thing ends up inside here. This Monte Carlo tree search not being tied to a specific game is a little weird, because once you start evaluating a game, it can only be used to evaluate that game from that point on. And honestly, you can't even like receive a random state, because if you receive a random state, I guess you can receive a random state depending on the way that you store it. Let's just try it, sure. Okay, so let's go back to the list. And for some reason, this decided to be full screen today. Why does it keep opening new files? Oh, I must have pressed like... Oh, there goes F11. Okay. Close that. Alright, so selection. Starting at the current state, select successive child nodes until a leaf node L is reached. So basically what we want to do is have this thing of states. Okay. Private. I'm going to say dictionary of iGame to this private class state stats. Okay, position stats. State stats. And this is public double, and we want visits get set. I guess we should follow the terminology that was actually in here. Oh shit, don't click on things. Increments, simulation count, and wins. Simulation count, simulations count, and public double wins get set. I'm using doubles here because the instructions say that on a tie you assign a half a win. Okay, then we have state stats, and this is what states. All right, now we're gonna say states equals new dictionary this. I must be missing an include, a using, whatever it's called in this language. Okay, so we now have all of the states for this game. It's almost a little frustrating putting it in here like this. Sure. Let's go to the actual game and make sure that tic-tac-toe is now going to have to like implement all of the things that make it hashable, which it has not done. So we want override I thought that would like autocomplete. Public override int get hash code. This is all right. There are nine. It's a tic-tac-toe board. There's 9 elements, and there are 3 states for each one. So we're going to say int hash equals 0, return hash. And then the way that we're going to do this is we're going to say for int I equals 0, I less than board dot length I plus plus. We're going to say hash equals times equals 3, and then we're going to say hash plus equals board of I. What are my options here? Player ID. Well, that sucks. Shit. Is player ID... What is player ID? Okay, sure, yeah. Player ID dot none equals 0. Player 1, player 2. That's it. Times int a board. So this is a player ID, which is 0, 1, 2, or 0, 1, or 2. And all we're going to do is come up with a unique value by multiplying it times 3 and then adding in the current value. So if you were to think of this in terms of base 3, why does this work? So this works because if you think of it in terms of base 3 instead of binary, your first digit is being assigned a value of 0, 1, or 2, which is always valid. When you multiply times 3, you are shifting left. And then you're adding in the next digit, and then shifting left, and then adding in the next digit. So this should always work and come up with unique values. Okay. So this hash code is correct. I have to look this up. C# override get hash code. Because I know you're supposed to do a bunch of things here. Overriding equals. Part 2. The importance of get hash code. Sure. 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 Overriding get hash code. Relatively unique result. Well, in our case, this is going to be unique. Get hash code. Great. Feel good about this. Get hash code. Okay, what's part 1 and part 3? Phone number. Reference equality. Overriding equals. Object equals. Phone number. Return number not equals null. Tuning our implementation. Okay. An overloaded version of equals that takes a phone number. Okay. Get type not equals get type. Overloaded version of equals. Goodness me, look at all this crap you have to implement. Are you serious? There's not like a button you press that just does this for you? Of course, if we're not concerned with performance, we can simplify this implementation a great deal. Okay. Public override bool equals. Whoa, look at that. The annotation for nullable reference types should only be used in code within nullable annotation context. The annotation? That's crazy. If object dot... Oh, that's interesting. It doesn't even have a... I thought it would be like a has value. I don't know. This is outside of my realm of expertise. Okay. Let's just do if object.reference equals if object equals null, return false. Reference equals null, return false. I think that's doing the same thing. And then this. Return true. How did we get this and number? Yeah, sure, okay. And then we basically just want to say if this dot get hash code, which I probably want to go ahead and... This is mutable, right? Is this mutable or not mutable? It is mutable. Well, that's not good. That's really not good. Okay, better question. Does it ever get muted? How do we say this? We say play game while not state.isTerminal get the current player, expand the successors, and then it must return one of those. Does expand successors must absolutely not mute. Expand successors. Oh, apply move is public. Okay, that's within it. Okay. Next state equals... No, we're copying it. And then every single instance of using board. Okay, so this is weakly not mutable. Weakly immutable. Which is not really that great, but we're going to go ahead and roll with it anyway. And we're just going to put a giant note here. Giant note. Maybe not here. Maybe, yeah, note. Assumes iGame is immutable. And then in here, to do enforce immutability. I guess in a sense this is enforcing immutability as long as you only have a reference to iGame, because you don't know anything about the actual game state itself. So you can't directly modify it. Okay, so actually I think this is better than I thought originally. Okay, back to the actual trying to do something. Okay, so now we have this iGame, and our tic-tac-toe state does this thing where we're basically just going to check the hash code. The reason I was checking that is because I wanted to cache the hash code, which is not safe. It's not safe to cache the hash code, but we're going to anyway, or this is going to be really slow. Okay, private int hash code equals -1. Okay, if hash code equals -1, then we want to calculate it. Okay. Now we can say get hash code equals object dot get hash code. And just return this actually. So as long as the hash codes match, then it's the same object. The annotation for nullable reference types should only be used within a nullable annotations context. I don't know. Does it build? That's my real question. Let's just Control C. Or does it complain? No, it complains. What if we just take it off? Can I just take it off? You gonna allow that? Does that build? Okay, that builds. All right. So we now have a get hash code and an equals implemented. And I honestly don't know which one of these is going to get called when we use it, but you know what? Those are implemented. You know what? Let's go read what part 3 was, just to make sure we didn't miss anything obvious. Overriding equality operators. Yeah, we should probably do that, huh? We can fix this by overriding the equals operator. Okay. Equals of tic-tac-toe and tic-tac-toe B. What are you complaining about? Requires a matching not equals to also be defined. Yeah, sure, we'll sort that out. Okay, so now what we have is a return A dot equals B not equals null. Oh, that is awful to read. If A equals null, return false. Return A dot equals B. Okay, a not equals. Oh, look, I used the equality operator inside of it. If object.reference equals A and null, return false. Probably, definitely, you shouldn't do that. And then this one is not of A equals B. Okay. Back to the Monte Carlo tree search. Okay, so first, it's select next action. We have this thing called a game stats. All right, this is all good. Now what we want to do is basically tell it number of simulations. And then we want int number of simulations. This dot number of simulations equals number of simulations. All right, so what that does is now we'll know. Okay, so step 1, selection. Step 2, close this. Expansion, simulation, backpropagation. Expansion. Step 3, simulation. Simulation. And step 4, back prop. Okay, selection. Selection. Start from root R and select successive child nodes until a leaf node L is reached. The root is the current game state. Okay, that makes sense. And a leaf is any node from which no simulation has yet been initialized. The section below says more about each round of Monte Carlo. Okay, so we need to do this n number of times. Okay. For int I equals 0, I less than number of simulations, I plus plus. Oh, crap all. So this is actually in here. And then I'm going to have a thing called private void run perform gosh, what is this? Let's just follow the terminology. Round. Perform round. Perform Monte Carlo round. And this is iGame current state. Current. Okay. And then here we have we just have perform Monte Carlo round of current. All right. Now all of these go in here. And then this thing right here says, okay, var successors equals current dot expand successors. And then we want to look them up in our dictionary. We want to look them up in our dictionary. And then choose the one that has the best overall score. Okay? Public double score is wins divided by simulations count. That was easy. So then we just say dot select states of M dot score. No. Dot order by descending M dot score dot first. Selected move. Return selected move. Using system.link. Okay. So all we do is we perform a bunch of Monte Carlo rounds. And then we say, okay, give me all of the successors, go find the one that has the highest score, and then return me that one. Yeah, that's it. Yep. Now I need to make sure that all this crap is in here. So we have current, all right, selection. Okay, find leaf. Private iGame find leaf. Perform selection. iGame current. Okay, find a leaf. Var leaf equals perform selection of current. Expansion. What was the difference? Oh, got it. So it's very possible so anytime we find a node that doesn't have all, that has a child that is not in the dictionary, we have found a leaf. True or false? True. Expansion is you make sure that all, okay. Find a node which does not have all children in the states database. Okay, expansion is make sure that node has all children in the states database. Let's just verify that my understanding is correct there. Unless L ends the game decisively for either player, create one or more child nodes and choose from one of them. Child nodes are any valid moves. Okay. So then we want var simulation root equals expand, expand of the leaf. So we want private, I think we want something like this. No, just an iGame. Expand iGame current. No, state. Sure. Simulation should return you back, okay, var states visited equals run simulation of simulation root, and then backprop is for each, no, var winner equals states visited. I'm gonna have to do this run simulation thing. Okay, private iGame array run simulation of iGame state is, doesn't really matter. All that really does matter is dot last dot current player's turn. I need to know who the winner was. Is terminal Oh, here it is. Winning player number. Okay. Player ID. Winner. That last dot is terminal out winner. For each var state in states visited, if now I need to look up the state, var stats equals states of state, and then I say stats dot simulation count plus equals 1, or really just plus plus. And then we say stats dot wins equals plus equals winner oh man, okay, this part is a little more frustrating. This part is a little more frustrating. Okay. If winner equals player ID dot none, okay, then stats dot wins plus equals 0.5 D. Else, if winner equals state dot current player's turn stats dot wins plus equals 1 D. Let's do plus equals 1. All right, so if, all right, at the end of the simulation we have the winner. It's either none or it's one of the other players. If it's none, we add 0.5. If it's a win, we add this. And I should wrap all this up, because we don't want to just do this in line when we didn't do the rest of it in line. Okay, we're going to do back propagation of states visited. Oh man, come on. States visited. And I think that's it, actually. Private void backpropagation of iGame states visited. And that's that. Okay, so we've done the backpropagation part. We need to do a simulation. A simulation is not that difficult. You just say var visited equals new list of iGame. Okay. Return visited dot to array, which I don't even really need to do. And then we can say, all right, while we can say visited dot add state while not visited dot is terminal. Whoa, no, state dot is terminal. Out player ID dummy. Then we can say var successors equals state dot expand successors, and then we want to randomly select one with equal probability. State dot okay, let's just have a choose random. Let's go private void random. And then I think I want something, okay, equals new random. And then I think I want something like private int next random. Nah, we don't even need this. Okay. And then we're going to say state equals successors of random dot next with a max value of successors dot length. And then we're going to say visited dot add state. Okay, that's a simulation, right? We take the states, we add the current one, and honestly, I don't even think we want to do this. Like, I think this wants to be void. And I think what we want is a list of iGame states visited. And we say state equals let's just do visited equal visited dot last. So run simulation is actually going to say visited var path expand path run simulation on this path, and back propagation, and I don't want perform selection, I want this to be a list. Expand. Void. So the idea here is we're just gonna, each of these like Monte Carlo rounds is us choosing a path through the thing and then updating the values all the way back up. But I need to track it all the way to the root. I can't just update that one little, starting from the end. So what I'm going to do is say, okay, perform selection, which is going to go ahead and... Oh, this is even more crazy. Huh. Selection. What is R? The root is the current game state, and the leaf is any node from which no simulation has yet been initiated. That is so interesting. The current game state maybe. The thing that's going through my head right now is whether we need a path all the way back to the root of the game, or if we just need it from the current state and then we can still make good decisions from just that point forward. And then when we play the second game, so the back propagation only goes back up to the current state. I'm having a bit of a hard time with this. Okay. I think we're just going to make it a path. And in fact, we're going to be really explicit about making it a path. We're just going to say var path equals new list igame of current. And then we're going to do perform selection of path, and all of these are just going to use path. Perform selection does not, okay, so now we're just going to have void and same thing here. Okay, so now the back propagation definitely works correctly. I feel like what I would want here is that simulations do make their way all the way back to the beginning of the game. Because if I'm playing this round and I like learn a lot about this one branch, I want that to propagate as high up the tree as possible. I don't want to have to explore every branch below this place. I don't know. I'm having trouble reconciling this one. Can you even know the path all the way back to the beginning of the game? Probably the answer is yes. Yeah, I think you can. I think you can. Is it valuable to do that? So basically, the way that I would do this is select the next action would take in the entire move history of the game up to this point. Not just the current state, but like... That doesn't seem right. Like from an... You could wrap it up in the state of the game. That's hard. Let's just keep going forward. Let's just keep grinding on this one, and then maybe this is a question where we can ask somebody that knows a little bit more than I do. Okay, so we have this path that we want to perform selection on. We want to expand. Okay, so expand is actually an easier one, which is really simple. We just say not state. We got to call these path. I guess we can call that visited, whatever. Let's just call them all path. It'll make more sense as we go. Path, path, path. Okay, so we have the state. And then we say var successors equals state.get successors, expand successors. For each var successor in successor in successors, if not states dot contains key successor, then we want to say states dot add successor new state stats, period. And then this needs to be simulations count equals 0. Oh, what's the question? You said you would put off a design decision. So, yeah, the issue here is we're doing Monte Carlo tree search, and I'm thinking of tic-tac-toe, right? On the first move, as we like walk the path, like when we're told to select the next action, we are given the current state of the game, right? And so the idea now is in Monte Carlo tree search, going back to here, that would be the root, whatever you were given, right? The root is the current game state. That's what it says. And then it says you want to like expand to a leaf, which is what selection does. It finds a leaf. Expansion then says, okay, I'm at a leaf. I need to add all of the possible children for this leaf. Or some way of determining that this thing is a leaf. Right? And select successive child nodes. How you select them isn't super clear. Although I'm going to guess that's what this is. But the question is, like, the real issue that I'm having is, you know, we expand these moves all the way down, and then in the back propagation step, we want to update the scores all the way back up the tree, right? But on the second move, we no longer have a reference back to the root. Meaning, no matter what we figure out from here down, we can't actually update the score at the root to determine, you know, like, is this a win or a loss for the original player. In a game like Tic-Tac-Toe, I don't think it's that big of a deal because there's just, you know, only 9 layers here. But in a much deeper game like chess, for instance, like, not propagating information back up to the root when you're halfway into a game provides you, like, it just feels to me like you're missing out on a lot of information that you could have, like, if the bad move you made was move number 3, how many games do we then have to play where we keep going down move number 3 and we start recognizing the problem at move number 7. We start recognizing the problem at move number 6. We start recognizing the problem at move number 5. Like, how long does it take for all of that information to make its way back up to the top of the tree? That's what I'm concerned about. And I don't know if what we should do is make it so that when it's time for you to choose, instead of just being given the current state of the game, you're given the entire path history of the game. Now, I know that really is only, like, doable for things like, board games and stuff, where you just have all the information about what a state is. But, like, in a world where there's, like, a ridiculous number of states, like, for instance, I don't know, playing a video game, like a first-person shooter game, you know, obviously just way too many states for you to keep track of all of them. Like, if you were to consider a frame to be a state, you would just, no way on earth you could keep track of all the frames. So I don't know. I'm just having a little trouble with, like, is it just the depth of the game determines how difficult it is to learn? I don't know here. Fair enough. I have never done this before, so you still have more information than I do. Monte Carlo algorithms are often memory stateless. Yes. Specifically, we're using Monte Carlo tree search, though. So, definitely not stateless. So, those two things could be your answer here. Like, in the grand scheme of things, doing it completely stateless makes total sense to me. Right? You're just like, let's play as many games as we possibly can, as fast as we possibly can, within some time limit, and then just choose the one that does the best. Right? That makes total sense to me. don't have to keep track of anything before it. But if we want to learn and we want to get better, we to some degree need to maintain, some amount of knowledge about what has happened before, some model to help us determine which moves to make. The first point means you will not have the path information in the root node. Right, I agree with that. But if you do decide to model the game, which we're doing, then you have the situation where how long does it take for information to get back to the earlier positions in the game? Or is that even a thing? So you'd have a secondary structure information algorithm. Yeah, right. Exactly right. Right now, all I'm doing is storing a dictionary of states we've been to with some stats about them. Maybe that's it. Maybe it's just within any give. Okay. So maybe we don't keep a model on the whole? Okay, let me think about this. Maybe we don't keep a model on the whole. Each time it's our turn to make an action, we clear out all of the information that we have from the previous rollouts. So this is like brand new each time we call the Monte Carlo tree search function. And then we always have this full game tree. It sounds like it. You want more information than Monte Carlo tree search. The Monte Carlo tree search will get you a one-time solution. Oh, okay. So then I do just clear this out. I just clear out the states that I've seen before. Okay. God. All right. That did not really come through in the reading. The application expanding the search tree based on a random sampling. Okay. This is a really crappy design then. So Monte Carlo tree search needs to be more of a static class. That's fine. I appreciate your help. Thanks, man. Okay. So we're going to do Monte Carlo tree search. This is not something we need to keep a hold to. It's going to be int num rollouts. Private int num rollouts. This dot num rollouts equals num rollouts. And then we're going to say Monte Carlo tree search dot search of current state num rollouts. To do, ideally, we verify that the successors that the result is in the successors. Okay, this makes much more sense. So we don't want this anymore. We don't want any of this anymore. And we want this to be search. I want this to be static. And we want this to be int number of simulations. Okay. Perfect. So now we have perform Monte Carlo. This needs to be static. This needs to be var states equals new. No, we need to call this tree equals new dictionary of iGame to state stats. We're going to call this tree. And we want to always pass in the tree here. Dictionary of iGame to state stats tree. Private static. You know what? I think what we're going to do is we're going to create a thing called a tree search as a private class. Okay. Private class tree search. And this is going to be private dictionary of iGame to state stats. We're going to call this states equals new let's not do that just yet. Let's go public tree search iGame current states equals new states.add current new. Okay. Now I want to move all of these into there. So I don't actually want these to be static. And I want this to be new tree search of current okay, we'll come back to this. So we're going to take all of these things, we're going to put them in this class. Really feel like that should have worked. Oh no, this is static. We want to make this public. We don't actually care about this anymore. Okay. And let's make this public. And this is going to be tree dot this. And then this is going to be tree dot states of m dot score. Okay. Wow. Okay. So if the simulation count equals 0, we want to give it a 100% chance of winning. Meaning that during the selection round, we will always choose that. Until we have fully explored every node of that tree. And I don't know if that's the right way to go about that or not. Maybe 0.5 is? Because we just don't know? Let's see, what would changing that do? If we set it to 0 and we found any other winning move, we would always go down the path of the winning move. Okay, that's bad. If we set it to, even if it eventually loses, or one of the other ones was the ones that's guaranteed to win. Because as soon as we found some positive value, it would then drown out the selections to go to any of the others. If we set it to 1, it will fully try every single one of the branches before choosing a different one. Okay. Was there any guidance in here about how to initially set them? Expansion. Rounds of search are repeated as long as the allotted time to move remains. Then the move with the most simulations made, the highest denominator, is chosen as the final answer. Interesting. I guess that makes sense. Why would you not care about the score? Because the one with the highest denominator had the highest score. Because that's why we kept selecting it. Sure. But why not just choose the one with the highest score? Not super clear. Yep, not super clear. Pure Monte Carlo. The basic procedure can be applied to games. Okay, that's not helpful. The main difficulty in selecting child nodes is maintaining some balance between exploitation of deep variance after moves with high average win rate and the exploration of moves with few simulations. The first formula for balancing exploitation and exploration in games, called Upper Confidence Bound 1, applied to trees, was introduced by these people. UCT is based on UCB 1 formula derived by these other people. And provably convergent adaptive multi-stage sampling algorithm first applied to multi-stage decision-making models, specifically Markov decision processes. Alright, these people recommend to choose in each node of the game tree the move for which the expression that has the highest value. Recommend to choose in each node of the game the first component of the formula. All right, well, we're gonna just follow the actual, like, I think we're gonna, when we create a new, okay, we're just gonna make it, we're gonna go public pure Monte Carlo score. We're going to say public state stats, and all I'm going to do here is initialize these to 0.5 in the crappiest possible way. Which is simulations count equals 1, D, and wins equals 0.5. To do, what should this be set at initially? Do I even need to set it? Do I even need to have it be part of the tree? Those are good questions. Okay. So now, the score will help us find whatever the next thing is going to be. So everyone's going to choose the best score for themselves. Right. And then, okay. To do. Is this how you actually implement expand? This forcefully adds nodes to the tree that do not have simulations. Okay, so I think that's my biggest question at the moment. And then right now the only thing left to do is say perform selection. And the rest of this, not score, denominator, which was simulations count. That's what it said. That is absolutely what it said. Which is still just bananas to me. Okay. To do. Why choose most simulations and not best score? best pure score. Right, so in Monte Carlo, the way I understand it is you are estimating the maximum likelihood of each move. So wouldn't you want to just use that likelihood to make your final decision? That's what this is. This is the final decision. Yeah, I just don't know off the top of my head. Okay, so we have this thing, this random right here. Now the only thing that we need to do is perform selection. So we're going to say var current state equals path dot last. Okay. While not state dot is terminal out player ID dummy. While it is not a terminal state, we want to, okay, var successors equals state.get expand successors. Okay. If successors.any states of m, no, states dot contains key of m if there is any missing successor, then we can just break, because alright, so this is saying get me all the successors. If there is any successor which does not exist in the tree, then we have found what we're considering to be a leaf. So we're going to bail. And then the next step is going to expand it and create the leaves within the tree. And then it's going to do the simulation. And otherwise, we're going to say var next equals successors. We're going to say state equals successors. That's the dot order by descending of state m states m dot pure Monte Carlo score, perform selection pure Monte Carlo. So this will have different selection techniques. Right now, this is the one that we're going to do. Pure Monte Carlo score dot first. And then we want to say path dot add state. I think that's it. All right, let's take a look at this. First, let's see if it builds. Okay, it builds. Okay, so you call Monte Carlo tree search, which is a static class. You're calling a static method, meaning that you're getting a brand new state every time you call this. You pass in the current state and the number of simulations that you want to run, because that is up to the actual player. Then you say, all right, create me a tree search object that we will then use. And then for the number of simulations that we want to do, perform a Monte Carlo round. Great. We perform Monte Carlo rounds for the number of simulations that we want to do. Then we select the best move based on the simulation count. This is literally following along directly with what's going on. Rounds of each are repeated as long as time is allotted. Maybe that's a better way to do it, is like allotment of time. To do. Alternatively, pass in an allotment of time instead of number of simulations. Okay. Then the move with the most simulations made, that is the highest denominator, that's the number on bottom, is chosen as the final answer. And that's what I did. The denominator is simulations count, which is on the bottom. Okay, so then it's the rollout part that actually matters. I feel fairly confident that this is correct. We're just saying perform this many rounds, choose the best move based on the denominator, return the selected move. That's pretty straightforward. This is an actual tree search. In the tree search, what we're doing is starting from blank. So each time we call to make a move, we're going to start from blank, and we're going to say perform a Monte Carlo round. That takes the current state, makes it the first step in the path, then it does a selection process. The selection process says get the current state, as long as it's not terminal, expand the successors, and if you find a successor that does not have, that one of the leaves is not contained within the tree, then we're considering that to be a leaf. And then we're saying as long as we have not found a leaf, we choose the best next state based on the pure Monte Carlo estimate, which is literally just taking the number of wins divided by the number of simulations. Okay, I feel good about that. Hey, Zeratar. Thank you so much for the raid, man. I really appreciate that. All right, my question for everybody who just got here. What was Zeratar working on? Fake answers only. We are working on Friday Fun Day, which is basically me doing something that has nothing to do with anything else that I've been doing, which is today Monte Carlo tree search. Peanuts? No, meatballs. He was exercising. Oh, that's a good one. What else was he doing? Fake answers only. Again, working on a meatball MMO RPG. Actually, I feel like that one was right. Is that fake? Is that actually fake? How was your stream, man? I hope you had a good stream today. Meatball cup. 2 meatballs, 1 cup. Ugh. He was doing aquatic yoga. That's good. You know what? Friday yoga, That does sound good. Let's all take a stretch. What else y'all get done? Going out for dinner, but wanted to. Can't tell yet. Since I want people to fake answers. Thanks for playing along, man. Appreciate it. Sphero Justice. That's kind of cool looking. Little guillotine. Nice. All right. So we just got to the end of like writing this Monte Carlo tree search for tic-tac-toe, and I'm reading through it to like convince myself that it works, and then we're just going to try it, and I'm going to play against it, and we're going to see if it like fails or doesn't fail. And then we're going to try and answer some of the hard questions that I came up with while I was doing it, because I don't know the answer to those. Guillotine the greedy cour. Ooh, interesting. Right. That's okay, man. Thanks for the raid. I really appreciate it, and I hope you have a good rest of your day and a good rest of your weekend. All right, so perform selection is go until you find a leaf. Thank you so much, Ardalis, for the follow. Oh, no, the raid. Goodness me, 2 raids back to back. Holy crap. Okay, Ardalis. Everybody from Ardalis's raid, please tell me, what were you working on? Fake answers only. Right now, we are working on Monte Carlo tree search over here. We're at the point of just having finished implementing it, and we're about to play it and see if it can beat us at tic-tac-toe. Roasting marshmallows. Oh, that's a good one. That's a perfect thing to do on a Friday. It's nice and chill here. I don't know what the temperature is like where y'all are at, but it is a nice fall day here. What else were y'all doing? Double entry accounting. Oh my god, that brings back chills. I don't even want to get into that. It's double entry accounting and gap analysis are the 2 things that I dislike the most. A site dedicated to hosting chicken streams. Oh my lord. A cucumber classification system using OpenCV and ML. That actually sounds like a lot of fun. That sounds like an incredible amount of fun. And hey, Surly Dev, how are you doing? Okay. You get successors. If you find a leaf, you break up out of here. If you don't find a leaf, you choose the one that has the highest score. You add it to the state. Oh, yeah, we reset the state. Then we add it to the path. Okay, great. Then we say, all right, now it's time to expand. We had a leaf. Hector HSC, thanks so much for the follow, man. I really appreciate that. I'm good, thank you. How are you? I am doing great. I'm doing really, really good. I'm having the best 3-week span in a long time. I started picking up and doing a couple of things that I had stopped doing for a while, and coming back to them after taking 10, 12 weeks off has just been really, really refreshing. The way that I was getting frustrated with the things, that's why I walked away from them. But coming back to them and realizing how much my brain has processed about those things in the meantime has been just really enlightening. And it's also good because a lot of it has to do with talking to people and whatnot. Doing a bunch of interviews and stuff. But it's been good. I also, things are going well at work. We worked on something for it must have been actively working on it since April. The project started in October of last year, and then we just sort of went and started. We were like, all right, we're going to collect a bunch of data, and then in April we started building models, and we went through some really rough times building the models. Then we made some progress, and now we got to the point where we're like, oh, we totally understand what's going on. Air quotes there. Totally understand. And we've just been making incredible progress toward a goal that we've had for a very long time. And it's quite refreshing. Things are just really going well. Walking away from stuff when stuck is always a good idea, right? Absolutely agree. I take breaks at lunchtime when I'm in the office just for the hell of going for a walk, even if I'm being productive. That is a good idea, yeah. I think like long-term breaks as well actually make a big difference. Like I said, this one was like 10 weeks where I walked away from this thing, and I guess it just depends on like your level of frustration with it, your inability to like see through it. I don't know what the right way to describe it is. Yeah. But yeah, it's just been good walking away. The whole like you run into a bug, you walk away. Yeah, that's like a 5-minute thing or a 10-minute thing. Sometimes I sleep on it. I love sleeping on it. But like I don't walk away from bugs for like 10 weeks. That's like something big has to be going on for me to walk away for that long. All right. What are y'all doing this weekend? Expand. The point of expansion is you have reached a leaf node and you need to make sure that all of the successor nodes are in the tree. That's my understanding. I think 3 in one day was the most. Oh, in my previous job, I used to measure my level of frustration by walks around the perimeter of the building. So I have a very similar measure, but mine was how many showers I take in a day. Because taking a shower is like the thing that I do when it's time for me to like walk away from the computer for a while. And in fact, right behind me here is a door. You can't see it because of the green screen, but there's a door right there that goes to the bathroom that has the shower. And yeah, there was like a little shower counter. I used to just get real high sometimes. Hey, thanks for the follow, John Calloway. I really, really appreciate that. What happened on the time when you had to walk around the building 3 days? If you even want to remember that, of course. 3 times. Expand. All right, now all of the successors are in there, so we run a simulation. When we run a simulation, we're not actually looking at the states. We're just choosing random moves until we reach a terminal state. They're probably, like in this case, this isn't going to be an issue for a board filling game like to do limit maximum depth. So for something like tic-tac-toe, this isn't really going to be an issue because, you know, you're guaranteed to have no more than 9 moves. But for a game like chess, probably even still not that big of a deal, although you can go back and forth. And no, it's still not that big of a deal. But there are some games where you can go so deep that you can't, like you can get yourself into an infinite loop in some games. So this isn't always safe. You need a way to bail out and then like estimate with a heuristic or something. We're just going to put a little to do there. I would kick boxes. Goodness me. That was your job, kicking boxes? What is... It's Friday and I can't even tell a joke. I used to shower at the end of the day when I worked at home previously. I started to keep a dictaphone on my shower, by the shower, because I would always think of stuff. No, I kicked boxes to relieve the frustration. Oh, yeah, okay. Well, that makes more sense. Yeah. I took up running recently. It's helped. It's helped a lot. But yeah. There was a phase too where I just started eating. And that did not help. But it was my birthday on Wednesday. And so I've got all of these cookies and brownies. Like, when it comes time for my birthday, I stopped asking for things and just started asking for food. Thanks, man. I appreciate it. But yeah, it was like crap used to just pile up, and it was always dumb stuff too, like stuff I was never going to use. Thanks, Funky Monkey. I really appreciate it. And also Surly Dev. Thanks so much. But yeah, so now I'm like, just give me gift cards to like Outback Steakhouse or, you know, wherever. And that's what I do. Like Christmas time, like January, oh, we're going out. Like we're going to just eat. We're going to have a good time doing it too. And then I don't have to worry about cleaning anything. Well, I mean, I do because I have kids. But, like, for myself, I don't have to worry about cleaning anything or anything like that. And you always get to try new stuff. Okay, limit the maximum depth. When it's terminal, we're going to bail. Cool. Then when we're done, we're going to back propagate. Back propagate. This is the part that I need to check the most. We have found a terminal state. We know that because we did this until we found a terminal state. Same in back propagation. We know we found it because it's a terminal state, and then we say who is the winner, which is what we got here. Then we go to all of the states in the path, and we say if the winner was nobody, you can go ahead and add 0.5. If the winner was somebody, then you need to only give the points to that somebody, the wins. But no matter what, for all of the states, you increase the simulation count because we saw that state. This is also probably a mistake. If you can visit the same state twice, it's counting twice, so don't do that. I don't even know if that matters to do. Okay, we're just gonna try this at this point. Kind of sitting here doing spinning. I just haven't wanted to run it, and now I do want to run it. How do I get to terminal, view terminal, view terminal, view terminal, terminal? .NET build. Oh, no, can't do that yet. Got to go to the program and make one of them a Monte Carlo tree search player. All right, the goal here. Oh, what are you complaining about? Oh, and we need to tell it how many simulations to run. 1,000 simulations, please. .NET build. So we as the human player are going to go first. You're going to see this and it's going to be like really crappy here. But basically the concept is it's going to print out all of the possible moves. .NET. That's not going to work. Alright, so what it does is, as the human player here, it prints out all of the possible moves and it tells you a number. Whichever number you choose is the one we're going to end up going with. You are using a Markov decision process together with Monte Carlo. Are you using a Markov decision process? I am looking at the previous state, a Markov decision process. I think my answer is no. I'm not entirely sure, though. There will be memes. Let's take a look. So basically, the way this started is I have never implemented Monte Carlo tree search before, so I literally went to Wikipedia and was like, let's see what we can do from here. And I read all of this stuff, and I read all of this stuff, and then I tried to implement it as closely to what it said as possible, and then we were going the pure Monte Carlo route. Oh, it's tree search. Got it. Okay. What is the difference, if you don't mind me asking? And don't feel like you need to go into too much detail. Also, thank you so much for the follow, Ciaran Bruin. That's the best I can do. I'm sorry if I missed it. Oh, geez, I turned my landing light on, and now my phone connected on my Bluetooth are coming out of the speaker on the bulb upstairs, and I can't hear you from the kitchen. What is that one website? It's Internet of Shit. How does it all work? Okay, we have a Monte Carlo tree search player. Now what we need to do is we need to make our choice. And I am just going to choose the top left. Our goal here is really for this thing to not lose to us. So I'm just going to try to win as hard as I possibly can. That's great. Key not found exception. The given key, tic-tac-toe, was not present in the dictionary. Okay, Monte Carlo tree search 97. Oh, yep, that's right. Okay. If... Alright, so when we run the simulation, we're playing a bunch of moves that we know are not in the actual tree, and we don't want to put them in the tree. We just want to ignore them. Is that true or is that false? I don't know the answer. Let's take a look. I think maybe we do want to put them in the tree simulation. No, I don't think so. I think we only want that one leaf. Okay. So if it's not in the tree already, then we don't care about it. So we're going to say if stats Markov decision process is kind of a framework for modeling reinforcement learning tasks, if that makes sense. I understand what the Markov principle is, where the current state only depends on the previous state, and I would imagine that since this is a modeling framework for reinforcement learning,